Welcome everyone, I'm Liz Payton with Western Water Assessment at the University of Colorado Boulder. Thank you for joining us today. Most of you have probably seen part one of our Snowpack Monitoring in the Rocky Mountain West webinar, so I'll keep this introduction brief. Western Water Assessment is an applied research program and is one of 11 teams in the NOAA Regional Integrated Sciences and Assessments, or RISA program. We're based in Boulder and Salt Lake City and work across the Intermountain West, Colorado, Utah, and Wyoming. Our speakers today are Gus Goodbody and Patrick Kormos. Gus is a senior hydrologist at the National Water and Climate Center, part of the USDA's Snow Survey and Water Supply Forecasting Program in Portland, Oregon. And Patrick is a senior hydrologist at the National Weather Service's Colorado Basin River Forecast Center in Salt Lake City. We're very excited to have them as guest speakers today to help us understand the role that Snowpack Monitoring plays in streamflow forecasting and to describe the streamflow forecasting methods and tools that their agencies have developed. The presentation will be recorded and last about 45 minutes, followed by Q&A. Please feel free to submit questions via the Q&A window. We'll be sure to share a link to the recording with you after the webinar. Now I'm going to hand it off to Ethan Knight, a researcher with Western Water Assessment, who will briefly describe some of the applications of Snowpack information before Gus and Patrick dive into the details.
Great, thanks Liz. In the Rocky Mountain West, snow is a dominant player in the hydrologic cycle. Across the states of Colorado, Utah, and Wyoming, where Western Water Assessment focuses its work, most of the region's annual stream flow, about 60 to 85%, originates as snowmelt. Since variation in the size of the snowpack from year to year strongly controls the magnitudes of seasonal, annual, and peak stream flows, monitoring the evolution of the snowpack over the course of the winter and spring is critical to forecasting stream flow. Snowpack information is applied to streamflow forecasts, the subject of this webinar, but also to several other applications, including ski resort operations and climate change studies. Snowpack monitoring can help with avalanche forecasting and the according risk assessments. Monitoring the snow water equivalent depth and density of snow on mountain slopes is important in assessing the potential nature of an avalanche if it were to occur. The changing dynamics of mountain snowpack and avalanches in the Rocky Mountain West are key proxies in assessing climate change impacts, as well as assessing risk and conditions for ski resorts, particularly in the backcountry in regard to avalanches. Snowpack monitoring is also useful for assessing the snow conditions of high mountain ecosystems and the snow-adapted and snow-dependent species that live in these areas, such as pikas and wolverines. Snow data are also used by biologists to study the impact of snowpack changes on animal migration. Lastly, snowpack data can also be used by atmospheric scientists to investigate cloud, precipitation, snowpack, and runoff cycles. Next slide. Next. Streamflow forecasting is highly valuable to water managers, users, utilities, and more in the WWA region, given its importance to decision-making processes in water management. Streamflow information will continue to become more valuable as water supply decreases and water demand increases in the West. The effects of climate change on available water supply continues to be an issue in certain regions of the nation, such as the Intermountain West. Inaccurate long-term streamflow information is required to determine the impacts. To help water management agencies prepare for climate impacts on water supply and do a more efficient job, more scientists are relying on computer models to forecast the amount of water that will be available for different time periods, such as weeks, months, or seasons. The delay between when the snow accumulates and when it melts is what makes it possible for hydrologists to use measurements of winter snowpack to make predictions of spring and summer streamflow. In some areas, however, snowmelt is not as dominant, and therefore forecasting is more difficult. For example, in parts of the Southwest, winter, spring, and/or summer rainfall can supply a significant amount of the streamflow volume. Because the source of this runoff occurs in the future at the time forecasts are issued, and thus cannot easily be predicted, forecast uncertainty is higher in these areas than in dominantly snowmelt basins. Water supply forecasts can vary in accuracy depending on the strength of the snowmelt component. Water users and providers in the region rely on forecasts of runoff timing and amounts made by the NRCS and the NOAA River Forecast Centers, or RFCs. Other entities produce streamflow forecasts, but the forecast guidance from these two agencies is the most commonly consulted in our region. And with that, I'll hand it off to Gus from NRCS. Thanks again.
Thank you, Ethan, and thank you, Liz. Okay. Yes, thanks to both of you for the opportunity to present here today. I'm going to go through water supply forecasting at the USDA, talking a little bit about our models and how we produce guidance and forecasts, and then also talking a fair bit about the applications and products that we produce and where you can find them. So just a little bit more about our organization. We're within the U.S. Department of Agriculture, Natural Resources Conservation Service. The Snow Survey and Water Supply Forecasting Program really focuses on data collection, and many of you are probably very familiar with that. Our SNOTEL network is probably our most publicly understood and viewed piece of our program. We also have a water supply forecasting portion where we develop seasonal water supply forecasts for many Western water supply forecast points. And there's a variety of products that we use to disseminate information both about the data collection and the water supply forecasts. Our program is administered through the National Water and Climate Center, which is located in Portland, Oregon. That's where I actually work. And then 12 Western NRCS state snow survey programs. So we sort of have multiple arms of the way we deliver and meet our mission. So connecting snowpack data collection and water supply forecasting, this may seem obvious, but the fact is that our SNOTEL data is used in a variety of ways now that are different than how it was originally designed. So our snow courses and SNOTEL networks were largely designed to support statistical water supply forecasting. And that really goes back to the 1930s. And I know Carl Wetlaufer, who works for the NRCS and presented in the first leg of this presentation last week, did a great job on the history, so I'm not going to go too far into that. But the important part to know is that a core component of our statistical models that we build and maintain for water supply forecasting, comes from our station-based data, primarily the SNOTEL network. Other things to know about our water supply forecasting program: our forecasts are largely for naturalized seasonal streamflow volume. And I bring that up because a lot of Western basins are regulated in the sense that there are either significant reservoirs or upstream diversions. In order to improve the skill in our models, we really want to remove those man-made effects as much as possible. So I'm just making it clear that by and large, our forecasts are for naturalized volume because that's what correlates best with the natural snow accumulation that we measure and use to predict. Our forecasts are published monthly, largely January through June. There's coordination with National Weather Service in some regions, although largely west of the Continental Divide, we've stopped coordinating explicitly in the last 10 years. We still collaborate closely with many of these river forecast centers. And then just to get an idea of the scale, the NRCS covers over 600 forecast points in the Western US and Alaska. So it's a large domain. As getting into a little more details on our models, and I'm not going to go too far into this, just to mention that our modeling techniques are different than what the Weather Service does. Our model guidance is based on statistical models, and we use principal component regression as our primary technique. We do consider external model sources, such as from the Weather Service, when we're reviewing and ultimately publishing our final forecast. And finally, it's important to know that our forecasts are not deterministic, but rather probabilistic, meaning in addition to a best estimate, we also provide error bounds. And that's a really important part of what we do, because water supply forecasting is fairly uncertain in a lot of cases, especially with the longer lead times earlier in the snow accumulation season. So statistical model primary inputs. SNOTEL and snow core, snow water equivalent, are the main pieces that go into our models. Water year total accumulated precipitation is another large and common input to our models. And then of course, we're using the naturalized streamflow data sets that we get from mostly from the USGS and other sources, and then we naturalize them based on the availability of reservoir or diversion data, and that's usually our target. So we're typically talking about April, July total volume, and we're predicting that using the snowpack and water year accumulated precipitation as inputs. In addition to those primary inputs, we also use, in some cases, additional predictors. Antecedent streamflow conditions can be one of these secondary inputs. So in basins where groundwater is of particular interest or a large contributor, we may use fall antecedent streamflow conditions to get a measure of base flow heading into the winter season. And in yet other basins, we may use climate indices, particularly in early season forecasts, where the skill of those climate indices actually is warranted. So statistical models for each publication date and forecast point. Well, that means that we maintain and operate thousands of different models. Common model forms, as I just mentioned, tend to be current SWE and water year precipitation. So for this most recent March 1st forecast, we would basically take our calibrated model, plug in the current snow water equivalent for the stations within the basin that we're forecasting for, or some subset of those stations, and also the water year precipitation to date to that point for those same stations. And then we typically calibrate for the most recent 30 years of data. So the statistical techniques are retrospective in nature, meaning they rely on long records in order to develop relationships between snowpack and runoff. The reason we use the most recent 30 years in a sense is to mitigate some of the non-stationarity issues that can be associated with statistical methods. So there's many different sources for non-stationarity. They can be from climate non-stationarity, which we know is a reality. They can be from station non-stationarity, so either where the actual ground-based measurements are made, the conditions there have changed over time, or it can be the sensors have changed over time. There's a number of sources there. And then there can also just be basin level non-stationarities, for instance, wildfire or something like that. So the hydrologic response from basins can change over time too. So limiting to 30 years doesn't really take care of all of those issues, but it at least keeps us in tune with the most recent conditions. And it is a balance between having enough samples to develop rigorous relationships and this non-stationarity issue. We can't usually build robust models just from a few years of data. So just to talk a little bit about forecast skill, and I know Patrick's going to talk more about this in the following presentation, but the primary uncertainty in forecasts in many of our basins is the future weather. So until we're able to predict the future long lead weather, it's very difficult, or I should say there's a bit of a ceiling on how accurate the water supply forecast can be. What I'm trying to show here is just sort of the best and worst case scenarios. So not all basins are created equally in this sense. So best model skill tends to come from snow-dominated basins where a higher proportion of the annual precip and snowpack comes earlier in the water year. That gives us a better chance to measure what's on the ground and relate it to what's expected later in the season. Conversely, worst model skill often comes from rain-dominated basins where the response, is quite immediate. There's not a lag between accumulation and runoff. Areas where there's highly variable interannual patterns of accumulation, or climatologically wet later in the year. So the map here is sort of showing proportion of spring and summer precipitation compared to the full water year. And you'll notice the blue tones, which are generally east of the continental divide, means that those areas get a higher proportion of their annual water budget through precipitation, whether it be snow or rain, later in the season. So by definition, those areas tend to have lower forecast skill. Conversely, on the west side of the continental divide, I mean, it's mixed. There's a mixed signal, but generally there's a stronger relationship, climatologically drier in the springtime, which is a better case scenario for statistical forecasting. Moving to the forecast delivery and products portion of this talk, I'm just going to touch on 5 main ways that we get our forecasts out and analysis tools that we use. Before I jump too far into that, I was just going to mention that our homepage, which is listed here, has a lot of information and links to these applications that I'm going to talk through. It also has additional information that's way more in depth than I have time to go into today. And for instance, the technical notes at the bottom here, if you're interested in more details about how we build our models or how to interpret them, that information is available through our website. So starting with the state water supply outlook reports, these are sort of the flagship reports of our program. They come out monthly, starting in January, typically. Excuse me. And these are a great resource. They're actually put out at the state level. So each state listed here publishes their own water supply outlook report, and it covers the basins within their state. It's a combination of information from snowpack information to reservoir information, and then the forecast information is contained in these reports too. So if you're not familiar with these or you haven't read them before, they're definitely worth taking a look at. The next piece I want to talk about is the National Water and Climate Center interactive map. Again, this is maybe one of our sort of highest visibility products right now. Carl Wetlaufer spent some time in the last seminar talking about how to look at snowpack and access snowpack data through this tool, which it's great for. Just wanted to highlight that from a forecast delivery standpoint, we also have all of our forecasts available. So whether they be current or historic, you can access all the forecast information that's in our database through this interactive map. The other piece I wanted to highlight here has to do with, in addition to just, hey, here's the current forecast, there's also a forecast error analysis section. So once the forecast season is over and the Streamflow data has been collected, you can actually come back in here and evaluate how the forecast actually panned out with regard to the observed Streamflow data. So there's quite a bit in this tool. It's quite powerful, and I encourage people to explore, and you can always contact me if you have questions about details of how to get what you're looking for there. The next piece is the water supply forecast chart. So I'm just showing the user interface for this, but this is essentially just another way to visualize the forecast that we put out. Pretty simple to navigate. Basically, you choose your area of interest and what date that you're looking for. Most people are looking for the most recent forecast, so that's pretty simple. There's some other user configurable options here. but essentially it's a different way to visualize the full forecast distribution by basin. So what we're looking at here is essentially, each forecast point has its own line, and then the full forecast distribution is shown in this rainbow bar, essentially, with the 90% exceedance being the lowest value and the 10% exceedance being the highest value. So there are several things that you can get from this visualization. One is the narrower the range from the 90 to 10% exceedance values, that indicates how skillful the model is. So the less range there is between those two values, the better from a forecast skill standpoint. And you can see in the Gunnison Basin here, there's actually quite a bit of variability across forecast points as far as what the skill is. And that's not atypical of other basins, and it can be for a variety of reasons, whether it be the availability of the information to feed the model, or it could be the hydroclimate, as we mentioned earlier. There's several different things that can actually influence how skillful a model is, even over relatively short distances within a basin. The final piece on this I wanted to highlight is that, similar to the interactive map, once the forecast season is over, you can come back in here and actually display what was the observed value for any of the publication dates. So in this case, it's this heavier black line. So you can basically see, okay, this was the forecast at that time. Where did the actual verification fall on that forecast distribution? Moving to the next product, we have the basin data reports, which are pretty simple, more legacy type, just tables of forecasts. So after we publish our forecasts monthly, we push those to our database, and these systems pick up and create these forecast tables, which you'll often see in the water supply outlook reports as well. And again, we publish the full distribution, so 90, 70, 50, 30, 10% exceedance probabilities, which just simply means that's the probability of at least of equaling or exceeding that value. And finally, I just wanted to mention our daily water supply forecasts. So this is a separate modeling system we have. It's fairly similar to the processes we use in our monthly forecast, but it runs unattended. What I'll say is that in these, there's a suite of products associated with the daily water supply forecast, and I'm showing two of them here. One of the main ones is the graph here in the bottom left. And I'll just note, it's basically showing for each day of the year, it's producing a forecast. And so you start to see trends where, things increase or decrease based on the sensible weather that's happened. The yellow boxes on these plots actually indicate what the monthly official forecasts are. And so our recommended use for this product is largely just as a trend. So since the last official forecast, are the water supply conditions, trending drier or wetter, essentially. So that's an important piece to bridge the gap between our monthly official forecasts. There's some other derivative products as well, like for instance, there's some map-based derivatives that include, in this case, it's saying how much have things changed since the beginning of the month. So again, this is a good trend. Hey, are things generally going down? It looks like west-wide, we've essentially had a drier than typical period since the beginning of March. So in many cases, forecasts are going down. That can change quickly with large storms coming in, like maybe the one that's coming to the Front Range of Colorado tomorrow or the next day. So that's sort of the end of my products and applications section. My last slide here is just a nod to sort of future directions for our program. We've done a lot of analysis in the last several years looking at our system and looking at ways to improve it. And we've we've basically settled on moving into with a new system that we're calling M4, and there's just a few bullet points here that highlight some of the new features of that system. So firstly, instead of relying on just a simple principal component regression model for each point, we're moving to generation of multiple models using multiple data-driven techniques. And then ultimately, we're looking at how do we combine the guidance from those different models into an official forecast. And the main reason we're really going this direction is I think there's pretty broad recognition that there's no single model that tends to be the best in all situations. And so there's a lot of value in having different techniques out there, whether those are done by the same agency or different agencies. There's a lot of value in different people working on the problem and different techniques being applied to the same problem. In the end, we're finding that combining of these multiple models into a single, even if it's a simple ensemble mean, can often outperform any individual model over time and under different circumstances. So that's an important direction. Also, this move to the new system will consolidate our monthly and daily forecast systems, which right now basically run separately. And with that, I am done with my presentation. Thank you again for the opportunity, and I think we'll deal with questions at the end of Patrick's presentation.
All right, thanks Gus, and thanks to Liz and Ethan for the opportunity to present to you guys for the second half of this seminar. Okay, I'm assuming that everybody can see my slide here and hear me.
Yeah, it's perfect.
Great, thanks Liz. Okay, well, I'm Patrick Kormos. I'm a hydrologist at the Colorado Basin River Forecast Center, and I'll be just kind of presenting the Colorado Basin River Forecast Center's snow data that's available and our water supply forecasting. I've set the talk up a little bit opposite to Gus, where I'll kind of start with the products and then move into the water supply and then talk about verification at the end of it. So I apologize for that. And real quickly, I've got the whole team here from our office on the bottom. Yeah, also I'm currently the forecaster in the lower green, the Duchesne, the Weber, and the Provo River basins. So real quick, I'll use a couple of acronyms. I apologize now. CBRFC is the one that you'll see the most, and I'll try to define them on the way through. So quickly, here's the chain of command. We're under the Department of Commerce, and under that NOAA, under that the National Weather Service, and then finally the River Forecast Centers. You can see this map here. The United States is divided up into major river basins, and the River Forecast Centers cover those chunks. So we are the Colorado Basin River Forecast Center, and we cover the Colorado River and Eastern Great Basins at our office. And we're in Salt Lake City, co-located with the Salt Lake Weather Forecast Office. So right off the bat, I wanted to kind of get these disclaimer points out of the way. We do not measure any environmental data from our office. We rely heavily on Gus's and the NRCS SNOTEL's outfit and USGS and other monitoring networks to get all the data that we need to run our models and make our forecasts. And the last bullet point is our main mission is to forecast stream flow both on the seasonal and daily time scales. So we are not necessarily a snow-centric group, but you have to get the snow right to make good forecasts. So in that sense, we cover snow. And here are those two forecasts real quick. Every day we run our model. We put out 10-day forecasts at 478 locations within our basins. And here's just kind of a sample graph. You can see the measured data in dark blue, and then the next 3 days in green, which we're pretty confident about, and then out to 10 days of these kind of purple dotted line. And then our water supply forecasts we put out in 174 locations monthly with some daily model guidance like Gus just mentioned. And we'll talk a lot more about this product later on. So real quick, we'll talk about what snow data we produce, how you can access it, and then jump right into our water supply forecasts, and then kind of do a wrap up with uncertainty and error and continued improvements in the office. So two major snow data products. One is the snow groups, and one is our model snow water equivalent modeled SWE. To get to the snow groups, you go to our homepage here. It's going to be on a lot of different slides. There's this kind of top menu that I'll mention a lot, and then there's these side drop-down menus for the interactive map. So to get to the snow groups, you kind of hover over this top snow menu and go down to Model Snow Group. Click there, and that'll take you to our snow groups page, which is essentially just a whole list of links. So you'll have to either browse through and find a basin of interest, or you can use the Control F search to find your basin of interest. There are two types of groups here. One is the CBRFC groups, the ones that we've created, and then there's a bunch at the bottom who are user defined. So if you want a snow group that we don't have, you can create it and save it, and then it's there for everybody to see. So real quickly, this is the snow groups page, and it's essentially just an index. So it's useful if you have a snow group that you look at day to day or year to year, and you compare it relatively to what it looked like before. There's a good disclaimer at the top of it. It says this is just a simple mean of SNOTEL groups. So when you get to the page, it right off the bat tells you what SNOTEL sites are in the group, and it'll plot the median from that snow group, last year's data and this year's data, where we are today. So this one here is the Gunnison River Basin group. It's got less than 10 stations. It's very interactive. You can choose what years you want to display. You can add or take out different SNOTEL sites. So let's see here. Here's just a zoom in of a bunch of the different options you can choose. And then at the bottom, after you're done making a group that you would like, you can type in a new name and save it, and it'll be on this website as well. So once again, mostly just an index. It doesn't like calculate SWE in a basin or anything. It's just a simple average of a bunch of different SNOTEL groups. And then kind of the more bread and butter of the Colorado Basin River Forecast Center is our modeled snow. So we run a lumped temperature index model over the Colorado River Basin. It's called Snow 17. It's actually a very interesting model. They started with an energy balance model and kept simplifying it as minimally as possible till the only two inputs you need are temperature and precipitation. Our hydrologic response units, acronym HRU, they're elevation based. So here you can see the East River at Almont Basin here is divided into 3 different elevation zones. Kind of the light blue is the low elevation zone, medium blue, middle elevation zone, and upper elevation zone, dark blue. And essentially we run this model once for each elevation zone. So the inputs we need are mean aerial temperature and mean aerial precipitation. The mean aerial precipitation, once again, relies very heavily on SNOTEL stations and other monitoring networks. And the mean aerial precipitation equation for these is informed by mass balance and PRISM. So essentially, we need to get enough precipitation to create the hydrograph and satisfy the mass balance. It's calibrated on 30 to 35 years of data. Every year we get 5 new years of data. We'll go in and make sure our parameters still make sense and we're still capturing variability in the model. And then every time we hit an even 10 years, we'll get rid of the previous 10 years. So we're always between 30 and 35 years, similar to what Gus talked about. Okay, there's lots of different ways to access this model from our website. So starting from our web page again, there's a snow conditions kind of drop-down menu on the right. And if you click on the grids tab in the middle and click on modeled SWE, You can choose the date, and this will present it on the interactive map in % of normal. And there's a nice big legend for you there. There's also an option to show all of the % of median basins or just the significant areas. And what the significant areas radio button does is it clips it to the areas of a basin that produce the most runoff. And what that essentially does is it gets rid of, say there's a lower elevation zone where the median value is 1 inch. All of a sudden, if you have 2 inches of snow there, it looks like there's 200% of median, but when in fact that really doesn't make that much of a difference in the hydrograph. And it's just a way to kind of clip it to the most significant areas. There's another tab here called points. If you click on that and then click show, you get all these squares, and these are the SNOTEL sites with medians that we show, and those are shown or color coded with the same exact way that the kind of gridded map elevation zones are shown. So you can quickly compare what a SNOTEL site condition is compared to our modeled snow water equivalent. Okay, the other way to access the data is if you go to this top snow menu and click on model snow, you kind of have to hover on snow and then click on modeled snow. That'll take you to our gridded maps landing page. This page has a lot of different things that you can access from it. So as soon as you click on that, model snow will be highlighted. However, there's lots of different basin condition maps here, monthly precipitation, water year precipitation, et cetera, mostly presented in % of normal. So once you make all your selections, you can select type, year, month, and then you can clip it to an area, the whole CBRFC, the Great Basin, Lower Colorado, Upper Colorado, or Utah. And then once again, whether you just want significant areas or all of the areas. Once you do that, you have the option to download the data file. So you can right click on that blue link at the top of the maps, and that'll download a text ASCII file that you can put into GIS. That way, if you don't like our kind of canned maps, you can make your own. So once again, for example, here's one of our maps that are available kind of daily. So this is % normal modeled basin for significant areas for March 8th, clipped to Utah, just as an example. So this is just kind of a real quick way to come grab a map, copy and paste it into any of your presentations that you want to show stakeholders kind of basin conditions and things of that nature. The last way that you can look at our data is relatively new, a couple of years old, and it gives the users a chance to really kind of dig down into the modeled snow. And to get to that, you have to click a lot. So on this right interactive menu, you click on the snow conditions drop down, and it gives you the 3 tabs. We already talked about points and grids. If you click on model, the model tab, and then show, it'll give you all these gray dots in the Colorado Basin River Forecast Center. And once you click on one of those dots, a little pop-up will come up and you click on view graph, and finally you end up at kind of our model snow page. So what we're looking at here is a plot of SWE in inches versus time, and this is the model snow for the different zones in our model. So automatically it'll pull up all of the different zones in the basin that you've selected. You can see in this drop down in the interactive map, it gives you the elevation zones of each, or the elevation range of each of those zones. You can also plot basin SNOTELs. So we've given you kind of a list of the basins that are in or near the basin of interest. There's also a place that you can add any SNOTEL in our basin that you want to. And then there's also just some interactive ways to add medians and minimum and maximums of the model results. So here's just an example of that middle elevation zone east at Almont, showing where we are today in our modeled SWE compared to the median values and then the maximum and minimum SWE from our model record. There's also options. You can look at SWE in inches or % of median. There's also a snapshot tool, so you can take kind of a presentation quality image and save that. Okay, that wraps up the kind of snow information portion of the talk. And so now we're just going to jump right into the water supply. So we'll cover what the water supply is, how we create it, and then a quick kind of look at verification and errors and ways that we can improve our water supply forecast. So the water supply forecast is an April through July volume. Most of them are unregulated, which I assume are very similar to what Gus called naturalized flow, not unnaturalized flow. And all that means is we're trying to present you with a volume of water that adds all the diversions and reservoir storages upstream. So it's a volume that you would have gotten if there was no water management upstream. These are issued at, like I said, 147 points in the basin. We give an official forecast monthly between January and June. They come out a little bit after the first of the month. And how we get this is we have a hydrologic model that sits underneath SNO 17. So we just talked about SNO 17 model, and that is on top of the Sacramento Soil Moisture and Accounting Model. There's another acronym, SAC-SMA. And essentially that controls the snow on top of our hydrologic model. So it matters that we do a good job modeling snow. If we have way too much snow, our water supply forecast is going to be too high, and vice versa. So like I just said, we have our SNO 17 model, which kind of feeds into the Sacramento Soil Moisture Accounting Model. And then we have a unit hydrograph model that takes those different zone outflows and creates a hydrograph with them. But for simplification, we're just going to call that the CBRFC model. So we've got a model here, and we've got model states here, and we've got model forcings here. So essentially how we make a water supply forecast is we take our modeled soil and snow conditions for today, March 11th, and then we take all the historical forcing data that we have for 35 years. So we'll take the air temperature and precipitation from 1981, from March 12th to the end of the water year, and we'll feed that into the model, and we'll get one hydrograph trace. And then for 1982, we'll take the air temperature and precipitation from March 12th through the end of the water year, and we'll feed that into the model, and we'll get a second hydrograph. And then we'll do that for 1983, 1984, and we'll do that all the way through 2015 till we have 35 hydrographs, which were forced with 35 different years of historical data. So from there, from our 35 hydrographs, we'll take the 1981 hydrograph and we'll calculate the volume of water that comes through that point between April 1st and July 31st, or April through July volume, and we'll get one volume. And then for 1982, we'll calculate that volume. So now we have two volumes, and we'll do that with all the 35 hydrographs until we have 35 volumes. From those 35 volumes, we kind of just summarize them in a box plot, essentially, and we present those as exceedance values. So essentially, these are percentile values, 90, 70, 50, 30, and 10. And how you interpret that is you have essentially a 90% chance to get at least this volume. And then you have a 70% chance of getting at least this volume. And then the median value is the most probable forecast. But there's only a 30% chance that you're going to get this high of a runoff and a 10% chance that you're going to get the volume represented at the top of the whisker. So we represent this in a couple of different ways on the next plot. Our official forecasts, we just kind of put a hot pink bar down through the middle of it. It ranges from 10 to 90. And then we put another pink dot at the 30 and 70, and then the middle pink dot is the median value. So for our official forecasts look like that, and kind of the daily model guidance, we just kind of use a blue line from the 10 to the 90 with kind of a dark dot in the middle that becomes a line. And these kind of go day by day. Every day you can look at the model guidance. So if that marches on day by day, you know, if you can just imagine this area as a bunch of vertical lines next to each other, what happens is you get this blue area. The top line is the 10th percentile exceedance value, and the bottom is the 90th percentile value, with this blue line being the most probable forecast. So, and then, yeah, when we get to an official forecast, we'll just throw the pink line on there. So what's that look like? This is called the evolution plot. This is probably our most popular water supply forecast product that we create. There's also simple tables that you can look at if this is too confusing. But essentially, here's that same blue area as the cartoon version on the previous slide. So the top of this blue line is the 10 percentile exceedance value, and the bottom's the 90. And here's our official forecast. So you'll see those at the beginning of each month. There's the January, February, and March 1st forecast. That blue line, like I said, we run our model every morning, so we just calculate the water supply forecast every morning as well. So that's the blue line, and that blue line marches forward every day on our website. Our graphics are updated. When you get to this plot, it's interactive, so when you hover over different parts, the legend populates. So you can see here the March 10th most probable forecast is 938,000 acre-feet. So you can hover over our official forecast volume. So if you hover over the pink line on March 1st, the legend will also populate with all the percentiles. The most probable forecast is 880,000 CFS. You can add our 7 days of forecast precipitation, which is here in this graph. So you can see that big storm coming in to Colorado is pushing the model guidance up, so you can see what storms are doing to the forecast. And then from here, you can start adding different things. You can add the maximum, median, average, and minimum as these horizontal lines. Once again, this is just a volume versus time plot. So these lines give you the minimum ever recorded. So it tells you in 1977, we got 283,000 acre-feet, but in 1984, we got 3.1 million acre-feet. So it gives you the kind of range of historic observations and central tendencies. The last thing you can do with this plot is you can plot the normal accumulation. So you can see this starts on April 1st and ends at the end of July. And this is just kind of the average accumulation and how the water runs off at the Gunnison and Grand Junction. Once we get to April 1st, we'll start plotting observations, how much water is actually running off from measurements, from streamflow measurements. So here's a plot from the same place, Gunnison and Grand Junction, from last year. And this is after the end of the year. So once you start marching on through April, every day, this kind of orange area accumulation plot will move to the right, and you'll see how much flow we've gotten. And you can easily compare that to kind of the normal runoff. So last year, we ran off much below normal starting at April 1st. The other thing is this horizontal orange line, and that'll give you the total observed. So when you're hovering back and forth, it'll give you both the values that accumulated up to that day and the maximum, the total observed for that time. So I know that that's a lot, and there's a lot that can be on these plots. I encourage you to look at them, use them, and please contact us if you have questions about how to use these. We're pushing for users to use our forecasts more probabilistically instead of just picking off the median. We would be happy to work with you on how to better use or better understand our water supply forecasts. Okay, so how do you get to those? There's two different ways from our main website. You can just go to the top and click on water supply. You'll get a map of the whole Colorado River Basin with these triangles on them, labeled triangles. The other way, on the interactive map, there's a water supply forecasts drop down. If you click on show, you'll also get those triangles on top of any map that you have. There's different options for our official forecast, the first of the month forecasts, or the latest model guidance, and those will just kind of color code the triangles according to this % of normal. Once you find the triangle that you like and you click on it, a thumbnail will pop up, and once you click on that thumbnail, you'll get to the interactive plots that we just talked about. So that's the water supply products. Let's talk about verification and errors and uncertainty. To get to the interactive verification map, you go, once again, you hover up on the water supply top menu here and come all the way down to historic verification map. Once you click on that, you kind of get to our interactive map shown here, color-coded in percent error. These are mean absolute percent errors from reforecast data. So this historical word that's selected here, the type, that says, you know, on average, how do we do? That's from lots of reforecast data, probably 30 years of reforecast data. So it gives you a quick color-coded map. You can click on them and get the exact number. And if you click on the link that comes up, you can dig deeper and deeper and deeper into our water supply verification. If you want to see how we did at an exact time, you can click on the water year and the month, and they will color code accordingly. So very similar to what Gus mentioned, we tend to do better in snow-dominated headwater basins with few diversions. We tend to do worse in low elevation, rain-dominated basins with unknown diversions. So that's the verification website data that's available to you. And if we look at that a little bit closer, let's look at where that uncertainty comes from. Our total forecast error from one of the dates that we give you a forecast is a combination of two different things: errors in the model and errors in the future weather, once again, which Gus did a very good job of explaining. So if we look at kind of visualize the total error as this bar height, we can divide that into future weather error and model error. Well, we can quantify these things. We can quantify the total forecast error from 35 years of reforecast data, right? We know what forecast we gave, and then we know what the observed volume was for those years, so we can kind of get a mean total error. In addition, we have a calibration time series for the last 35 years, so we can see what our model said the volume should be and what the volume actually was, and that quantifies the blue bar. So then we can get the error due to future weather just by a simple differencing. And I'll quickly go back and say that, you know, this model error is due to lots of different things. It's hard to split apart the different components of the model error, but that's due to, you know, errors in our model soil moisture, errors in our modeled snowpack. They could be calibration errors, so maybe our model parameters are wrong, or just specifically, you know, model structure. Maybe our model isn't complicated enough to accurately simulate the hydrology.
Hey, Patrick,
okay,
not out of time, so thank you.
Okay, great. I will quickly go through this last two slides and then wrap it up. Thanks, Liz. So we've done a quick exercise on our April 1st forecast, and the bottom line is essentially half of that is due, half of the error in an April 1st forecast is due to weather, and half of it is due to model errors. We're doing lots and lots of stuff to try to improve our model. We're trying to address future weather uncertainty and model errors. And one of the things that have been very popular and people have been looking at are external snow products that people are putting out. So as a quick thought experiment, you know, even if we got a perfect snow product from somebody, that would address a portion of the model error, but none of the portion of the future weather error. And it's very hard, like I said, to divide this up into how much of that model error a perfect snow product could provide us. You know, it could range between 5 or 95%. So with that, I'll leave you guys with kind of our contact list, and thank you again for the opportunity to talk to you about the Colorado Basin River Forecast Center's water supply and snow products. Thanks, guys.
Thank you. So thanks so much, you guys, Ethan, Gus, and Patrick, for these fabulous presentations. And thanks also to those of you who have already submitted questions through the Q&A box. Please feel free to keep them coming. There aren't very many questions, and there were some that came in that were answered during the course of your presentation, so those sort of went away, which is awesome. So let's see what we've got here. We only have a few minutes, but here's a question. Can you touch on the topic of practical metrics on the horizon or currently incorporated for increasing some of these forecast skill, especially soil moisture? And it's for either of you. It says for either Gus or Patrick, so.
I'm not sure.
I'll
Did you repeat the question? And then
Yeah, I
Pat can
think
start.
that they're trying to get at what's on the horizon for increasing some of the forecast skill, especially soil moisture. Maybe if you could address what folks are looking at as far as improving the soil moisture component of the forecast.
You want to start with that, Patrick?
Sure, I will. We've got the Colorado, I forget what it's called, Hydrology and Climate Working Group has that set as a high priority to investigate. For our model, we are unaware of products that can handle the depth of soil moisture that we envision needing, or the spatial heterogeneity of soil moisture. So all that to say, you know, Gus might be able to better address that, but you know, we have a calibrated model. We don't believe that there are sufficient soil data now, nor are we aware of products coming down the pipeline. There are lots and lots of things that address other portions that increase skill. There's a lot of work being done on seasonal to sub-seasonal weather prediction, which would of course give both Gus and I a window into future weather. We're doing current work on climate indices, so maybe we can wait kind of those historical years that we run through the model to get our forecast. But those are kind of the data-driven indexes that would hopefully advance. Gus, you want to?
Yeah. So NRCS measures a lot of soil moisture. I mean, it's like Patrick mentions, it's not super deep, so it's relatively shallow. We've already experimented some with using those data directly in our statistical models, and we think there's a lot of promise for improving forecasts. I would just mention though that, you know, soil moisture is an important piece of the equation. It's not the primary driving force of water supply. It's kind of back to the, you know, total basin moisture input through precipitation and snowfall is really the main driver. And then the soil moisture would essentially tweak, you know, the predictions up or down to a smaller degree, but yet very important. And in fact, we're in one of those years right now in a lot of the Colorado Basin as it is. We have extremely low soil moisture conditions and low groundwater or base flow conditions. And so, you know, we get into sort of this multi-year drought situation where those factors start to become more important. And also those factors are more important in basins that tend to be more arid because it represents a larger portion of the total water budget. So, but yeah, it's there. We actually have a few projects going on related to this exact question of how to, one, get a soil moisture data set that would be usable, and then two, you know, how do we actually build it into our models in a meaningful way, you know, with the type of responses that you'd expect.
Well, thank you so much, you guys. We're about out of time. So thank you for joining our webinar, and thanks to Ethan, Gus, and Patrick for their great presentations and for answering our questions. That ends part 2 of our 2-part webinar on the Snowpack User Guide. We hope you have enjoyed learning about the Snowpack monitoring, and we would love to hear from you about how you might use the Snowpack User Guide or how it could be even more useful to you. You can download the full guide and view other resources on the Western Water Assessment website. Ethan has posted a link in the chat box. We'll also be posting a recording of this webinar on our website, and we'll send you the link when it's posted. In the meantime, please feel free to reach out to any of us if you'd like to follow up. Thank you.